Welcome back. Yeah, another leg of our journey. I can't believe how fast we're traveling. We're going far, far faster than the speed of light, which is, of course, as you might find out in week 6, something really impossible in real life. But there you go. Maybe I know a few shortcuts in my space-time machine that could possibly explain it. So we're going across the universe. Now, we've already learned how to conquer gravity. We've left the Earth. And we found out what will be find orbiting the sun alongside the Earth in the first week. No, second week that was, wasn't it? How tired were you having fun? Where the solar system sits with all the other suns and solar systems in our galaxy. And this week we're going to leave the relative safety of our galaxy and set off into the universe itself. And we're going to find out all about the universe, where it came from, how long ago it was formed, how much longer it's going to exist, how long it will find its end, because it will end at some point. But first, let's find out how big the universe is. Now, for those of you who have ever read the book called The Hitchhiker's Guide to the Galaxy, you may do, because it is on the GCSE reading list, so if you're lucky enough to be in the year that does it. It's an amazing book. It's very funny. It's about a man called Arthur Dent, who is on the Earth one morning, and his friend, who turns out not to be from London, Guildford, but turns out to be an alien, takes him off the planet just before for a hyperspace bypass. And it's about his adventures. But one of the things that Douglas Adams says at the beginning of the book is really rather incisive. He said, as the book opens, that space is big. You just won't believe how vastly, hugely, mind-bogglingly big it is. I mean, you may think it's a long way down the road to the chemist, but that's just peanuts to space. And it talks about the size of the universe. Now, that's one way of saying it's just a long way. But when we talk about the universe, we need a way to explain how big it is without using actually kilometers, miles, meters. So in order to describe the universe in terms of size, we need a special way of measuring it that isn't in kilometers or miles or meters, because the distances are just too big, and we'd need numbers so big that they would be effectively meaningless, and they'd be difficult to work with. So we need something called a light year. Now, a light year. What's a light year? Well, a light year is the length of distance that light travels in 1 year. So that's where we are. So in order to describe vast distances, we don't use kilometers, miles, meters, yards, whatever you want to use. We use the distance that light travels in 1 year. Now, we can also use light minutes, because sometimes it's easier to say how close something is on long distances. So light minutes, so light will travel 17,987,547 kilometers in 1 minute. Even in a second, light is going to travel 299,793 kilometers in 1 second. And the moon is actually 1.2 light seconds away from Earth. So that means when a beam of light leaves the Earth, the moon, comes from the sun, it touches the moon and it reflects back to us, because that's what moonlight is, remember, it's reflected sunlight. The light from the moon takes 1.2 seconds to reach us. So if the moon was to suddenly disappear, we would still see its light for another 1.2 seconds. And the sun is about 8 light minutes away from the Earth. So if the sun was to switch off, we wouldn't know about it for nearly 9 minutes, 8.5 minutes, which is incredible if you think about it. So remember, a light year is the distance light travels in 1 Earth year. 1 light year is about 6 trillion miles. That's 9 trillion kilometers. That's a 6 or a 9 with 12 zeros behind it, which is incredible, really. And you've got to remember that because the universe is so big, light still takes a long time to travel across. We'll find out later. So when we use really powerful telescopes to look at distant objects in space, we're actually looking back in time. Now, how can this be? Well, if light travels at a speed of 300,000 kilometers per second, 186 miles, 1,000 miles per second, it seems really fast. And it is really fast. If you could travel that fast, you could get anywhere pretty much instantaneously on Earth. Nobody would see you arrive. You'd suddenly appear. But objects in space are so far away. The universe is so big that it takes a lot of time for the light to reach us. And the farther an object is, the farther in the past we see it. Now, our sun is the closest star to us. So it's about 93 million miles away. So the sun's light, as I say, takes about 8.3 minutes to reach us. Now, that means that we always see the sun as it was about 8.3 minutes ago. We're looking at the sun in the past. Now, the next closest star to us is 4.3 light years away. So when we see the star today, we're actually seeing it as it was 4.3 years ago, which is 2016. So the light we're seeing from our nearest star left there nearly 5 years ago, 4.3 years ago. And all of the other stars we can see with our eyes are even further away. Some are even thousands of light years away. So we're looking at stars as they were thousands of years ago. Now, we've already found out that the solar system is some 180 times bigger than the distance from the Earth to the Sun. So if you can imagine the distance from the Earth to the Sun, and then multiply that by 180 times, then that is the size of the solar system. Let's have a look at the next slide. Now, the Milky Way is actually 100,000 light years across. Now, there's somewhere between 100 and 400 billion stars in our galaxy. And as I say, it's 100,000 light years across. So that means if I switch a light on one side of the galaxy, it's going to be 100,000 years before someone at the other side of the galaxy notices I switched the light on, which is a long time. Now, that means the galaxy is pretty big, 100,000 light years across, millions and millions and billions of miles across. You just can't even contemplate how big that is. So, the galaxy, as we know, is one of about 20 in a little group of other galaxies called the local group. As you can see on the screen there, we've got one or two different ones there. Some have got funny names, NGC, whatever. Some are called names, like ours is the Milky Way. Andromeda is the closest proper galaxy towards us. Then you've got nebulae, like galaxies like M33. You've got the Magellanic Clouds, one called Fornax. They're all galaxies, and they're all clustered together in a little group. Now, this is where space starts to get incredibly big. It's about 3 million light years across. Again, if I was to go to the edge of our local group and shine a light across towards the other edge, it would be 3 million years before someone realized, again, I'd switched a light on. But even that local group is dwarfed in comparison with the next group of objects, which is called the Virgo supercluster. Now, the Virgo supercluster, as you can see on the screen now, is a mass concentration of galaxies, and it contains the Virgo cluster and the local group, which in turn contains the Milky Way and the Andromeda galaxy. At least 100 galaxy groups are located within its diameter, 110 million light years. This time, light will take 110 million years to travel across the distance. Now, the Virgo supercluster is one of about 10 million superclusters in the observable universe. But even that is not where our story ends. That's not the entire universe. Because the Virgo supercluster itself is only part of an even greater supercluster, Laniakea, a galaxy supercluster that's home to the Milky Way and approximately 100,000 other nearby galaxies. And it's some 520 million light years across, 500 million light years. That means that if I was to go to the left-hand side of that, shine a torch right across the middle to the other side, switch a light on or fire something off at the speed of light, it would take 520 million years for that light speed message to go across the width of there, which again, I think you'll agree is an incredible distance. So the universe is what comprises of superclusters. Now, those superclusters are actually barely distinguishable. It's not obvious where they end and merge or meet. Some of them are spread out, some of them are close to others, but we can still see that there are sort of superclusters. And it's not possible to know how many of these superclusters there are, because the universe is so big that it's not been around long enough for light to reach us from some parts of it. In fact, the light from the furthest reaches of the universe will never reach us. The universe itself is actually expanding. It's getting bigger and bigger, and it's getting bigger faster than light can travel. It's a bit like trying to run up some really fast escalators. No matter how quickly you run, you're never going to get to the top. And it's this fact that, once discovered, led us to a theory called the Big Bang Theory. Now, you may have heard of this before, but what is it? Well, for a start, it wasn't particularly big, and it wasn't particularly much of a bang. There was no real explosion as such. Well, not to start with, anyway. Now, the Big Bang is how astronomers explain and scientists and physicists explain how the universe began, the way it began. And it's the idea that the universe began as a single point. And that single point stretched and expanded to grow as large as it is right now. And it's still stretching. So what's this Big Bang all about? Well, this guy here on the screen is somebody called Georges Lemaitre. Now, in 1927, he had a big idea. He said that a very long time ago, the universe started just as a single point. He said the universe stretched and expanded to get as big as it is now, and that it could keep on stretching. Now, we know the universe is expanding because the light from the stars has been shifted, moved towards the red end of the spectrum. Well, what does that mean? Well, light is a wave. Now, there's a phenomenon called the Doppler effect. Now, the Doppler effect is that thing you hear when a motorbike or an ambulance, a police car with a siren going goes past you. You've probably noticed that the siren appears to change in pitch as it goes past. When it moves away, the siren sounds lower in pitch than when it is moving towards you. And it happens with all waves, including light waves. If you have a light source that's moving very, very fast, then the light can look as though it's getting compressed. It isn't, it's the same, but because you're moving, energy hit you ever so quicker. So it appears to your eyes or your ears that the sound is compressing. And when it's moving away, it sounds like it's getting lower, or it stretches out to the red spectrum. So we can look at the Doppler effect when it comes to light as well as sound. Now, as we just saw, the universe is a very big place. I mean, that's an understatement. It's enormous. It's everything anyway. It's been around for a very long time, relatively speaking. So thinking about how it all started is really hard to imagine. Okay. Now, a couple of years later, after Georges Lemaitre came up with his idea, a guy called Edwin Hubble. Now, Edwin Hubble was the guy who the Hubble telescope was named after. Now, he noticed that other galaxies were moving away from us, and that's not all. The farthest galaxies were moving faster than the ones that were closer to us. So I'm just going to, somebody's got their microphone on, so I'm just going to have to mute, because all I can hear in the background is them. No, that's it. I think it's gone now. Okay, super. Yeah, Edwin Hubble. Now, we've already heard that meant the universe was still expanding. Because all the galaxies, every single galaxy, wherever you look, pretty much everything's moving away from us. And if you went somewhere else in the universe, everything would look like it was moving away from you. So we know that the universe is expanding. It's like if you drew some dots on a balloon and then started to inflate it. The dots would move apart, although the dots themselves are not moving. It's the balloon that's expanding. And that's what's happening in the universe. The universe itself is expanding, and that means the distance between things is getting greater. That's why things are moving away from each other. Now, it's just like Lemaitre thought. And if things were moving apart, it meant that long ago, everything had been close together. If you think about it, if something's moving away from you, then if you go back in time, it must have been closer. And then you go back a little bit more, it must have been closer still. So there must have been some point in time where everything was really close together. And when I say really close together, I mean everything that we know now was in a very strange form. There was no matter, no energy, but what became matter and energy was still there, but really crushed down, if you like, into a tiny point of nothingness called a singularity. And everything we can see in our universe today, the stars, the planets, the comets, the asteroids, they weren't there at the beginning. So where did they come from? Well, the Big Bang. The universe began, it was just a hot, tiny particles mixed with light and energy, all crammed together. It was nothing like what we see now. It's as everything expanding and took up more space, it started to cool down. All that hot, dense energy started to expand out, and things started to cool down. So just after a fraction of the tiny second after the Big Bang happened, everything started to spread out, as you can see there in that first little bubble. And then it started to expand and expand. So those early bits of tiny particles started to group together. They formed atoms. And then those atoms grouped together. And over lots of times, the atoms came together to form stars and galaxies. And then you can see in the second little circle on there, the inflation happening about 380,000 years after the Big Bang. And the groups of atoms became molecules, and oops, here we go, Eden's arrived. Let's just admit Eden into the lesson. Right, that's brilliant, we are all here now. So yeah, after the Big Bang, about 380,000 years after the Big Bang, we're starting to see things coming together, and the universe still isn't like it is now, but it's got the very early stages. It's like a box of Lego. Okay, can you imagine all of the plastic in the Lego was crushed down into a tiny little ball of plastic, and all the color was separate. Then all of a sudden that expanded, and suddenly you got different colors of dust in different places, and gradually the dust of the plastic collected together and started to form the bricks, and then the bricks came together to start forming the objects that we're around. That's a bit like that, if you can imagine, but instead of plastic and dust and color, we're talking about energy and matter and protons and neutrons and atoms and everything. It must have been an amazing time. You couldn't have survived there. If you go back there, you just wouldn't exist, because the universe would be just weird. You couldn't be here. So at the same time that this was going on, stars were being born, and at the same time galaxies were crashing and grouping together, and new stars were being born and dying, and then things like asteroids, comets, planets, and black holes formed. And eventually we got to how the universe is today, but of course it's still expanding. But it got so big and it led to such great things. Some people call it the Big Bang, but maybe a better name would be the everywhere stretch. I don't know, what do you think? So we can see this happened a long time ago. So how old is the universe? Well, we don't know the exact age of the universe. For a start, we think it's about 13 billion years, give or take a few billion. Now, astronomers estimate the age of the universe in two ways. One, by looking for the oldest stars. Two, by measuring the rate of expansion of the universe and working backwards to the Big Bang. So we can look at the old stars, or we can look at how things are expanding. Those are the two ways we can age the universe. Now, the first way, one way astronomers estimate the age of the universe by studying collections of stars known as globular clusters. Now, a globular cluster is a dense collection of roughly 1 million stars. Now, since all of the stars in a globular cluster formed at roughly the same time, they can serve as kind of cosmic clocks. And that's the first way we estimate the age of the universe. It's based on our understanding of the life cycle of stars. We already did this in a previous lesson, remember. Now, the life cycle of a star depends upon its mass, remember? Supergiants, red giants, black holes, white dwarfs, all that stuff. Now, stars with a higher mass, that's those that have got more hydrogen than others, are much brighter than lower mass stars with less hydrogen. Now, high mass stars rapidly burn through their supply of hydrogen fuel. Like a star like the sun has enough fuel in its core to burn at its current brightness for approximately 9 billion years. It's about halfway through that at the moment. Now, a star that's twice as massive as the sun, that's going to burn through its fuel supply in about 800 million years, a lot less. Now, a 10 solar mass star, that's a star that's 10 times more massive than the sun, burns nearly 1,000 times brighter and has only a 20 million year full fuel supply. Now, conversely, a star that is half as massive as the sun burns slowly enough for its fuel to last more than 20 billion years. So if a globular cluster is more than 10 million years old, then all of its hydrogen-burning stars will be less massive than 10 solar masses. Now, that implies that no individual hydrogen-burning star will be more than, say, 1,000 times brighter than the sun. Now, if a globular cluster is more than 2 billion years old, then there will be no hydrogen-burning stars more massive than 2 solar masses. You see how we're looking at the different stars. And by looking at how many stars are in there and where they're burning, we can tell how old they all are. Now, the oldest globular cluster contains only stars less massive than 0.7 solar masses. Now, these low-mass stars are much dimmer than our sun. Now, this observation, when we look at it, this suggests that the oldest globular clusters are between 11 and 18 billion years old. Now, the uncertainty in this estimate, because we can't be 100% sure, so that's a wide range, isn't it? You think about it, 11 and 8, that's 7 billion years error in there, okay? So this estimate is due to the difficulty in determining the exact distance to a globular cluster, and in our ignorance of some of the details of how stars evolve. So basically, we don't know enough about stars. We can't accurately measure the distance. That's why we say it's somewhere between 11 and 18. Now, that's not really good enough, is it, if you think about it? Because that makes a lot of difference over time. 7 billion years is a long time. A lot can happen, even in the universe. Okay, so an alternative approach to this estimate, to the age of the universe, is to measure the current expansion rate, so how fast it's expanding, and use that as a measurement to trace the expansion back to the Big Bang. So we know where we are today. It's a bit like saying, I don't know when that car left the house, but I know it's on a road and I know it's traveling at this speed. So I can work out backwards when it left home. And that's what it's doing with the stars. We know the stars are like that today, they were like that the day before, they were like that the day before that. We can then trace that back and we can work out how long they've been expanding. And if we know how long they've been expanding, we can tell when the expansion started, and that is the Big Bang. Now, this depends on a number of possible ways in which the universe is expanding. Oh, no, you say. What do you mean, a number of different possible ways? Well, because expansion can happen in different ways. Oops, expansion. Now, depending on whether the universe is decelerating, slowing down, expanding uniformly, that's getting bigger at the same rate, or accelerating, puts the age of the universe between 9 and 11.5 billion years old. So now we've got one system saying it's between 11 and 18, and one saying it's between 9 and 11 and a half. So if we use both methods and allow for overlap and some of the things we're not sure about, we get a pretty good estimate of about 12 to 13 billion years. Now that's a lot better than between 9 and 18. That's between 9 and 18. That's basically twice. The difference is twice what the lower value is. That's rubbish. That's a bit like saying I could be 50 years old or 100 years old. I'm somewhere between the two. Great. That doesn't help me because 50 years old is one thing, 100 years old is something else. So if you say the universe is either 9 billion years old or 18 billion years old, it's not really helpful. But we narrowed it down by using two systems between 12 and 13. Now that's better. That's a bit like me now saying I'm somewhere between 50 and 100. Well, I'm somewhere now between 50 and 60. Now that's a little better, isn't it? But we can make it better than that, because what's happened is NASA have been doing North American Space Agency, National Agency for Space Administration in America. They've been doing some measurements with spacecraft, and they've come up with the age of the universe as 13.7 billion years old, plus or minus about 130,000 years. Now that's a bit like me saying I'm somewhere between 55 and 57. Now that's a lot easier, isn't it? So now you know a little bit about more how old I might be. Okay, right. Now I want to introduce you to something which is a discovery which was a real pain in the neck when it was first discovered, because it was getting in the way of some serious observation, but it turned out to be one of the most important scientific discoveries of the century. It's called cosmic microwave background radiation, or CMBR. Now, what's cosmic microwave background radiation? Well, basically, CMBR is an energy that's left over from the Big Bang, okay? So this precise dating of the universe and a lot more besides was found out because the source of energy that's been hanging around since the very Big Bang itself, the cosmic microwave background radiation, and it's the radiation from the very beginning of time itself. You can hear it for yourself if you want to. Get a television or a radio and then tune it in if you've got one of those old radios with a dial, and then turn it around so you can't hear the music or the speaking and you hear that hissing sound. Or if you're on a TV, you get that white noise. If you unplug the aerial and you get that hissy noise, that sort of white stuff and the noise going on in the background. That is cosmic microwave background radiation. Okay, so will the universe last forever? Well, there are 3 ways in which the universe could end. Well, it's going to end. We know that. It's either going to be by something called the big freeze, the big rip, or the big crunch. And it all depends on gravity. Our old friend gravity again. Okay? If it wasn't for gravity, there wouldn't be a universe. And if there wasn't for a universe, there wouldn't be gravity. The expanding force as well, because gravity is trying to pull everything together, but there's another expanding force that's pushing things apart, the thing that's driving the universe to expand. Okay? And that comes from some missing energy, what is called dark energy. Okay, so if the universe is expanding steadily, then the dark energy causes the gravitational energy to be stretched until it no longer attracts the stars and galaxy. And the universe will expand until the force of gravity no longer applies to galaxies and stars. They'll be pulled apart until the stars sit in isolation with their light redshifted. So all the stars will be all on their own and you will never see any other star at all. They'll be stretched out. That's the end of the universe. The stars will be so far apart from each other that they will have no interaction whatsoever with another star, and they'll eventually just burn away and be left as dead stars everywhere. That's one way the universe will end. It's a bit like an elastic band. If you stretch and stretch and stretch and stretch until the elastic band just gives up its stretchiness. Okay? Now, if it starts to expand ever faster, in other words, it's an accelerating universe, it will not only overcome gravity, but that force will win over the electromagnetic and weak and strong nuclear forces. Now, those are all the forces that hold the actual atoms together. And it won't just be the stars that are left stretched out across the universe. Every single particle will be so far apart from the next, they will never meet. Every atom will be split into protons, neutrons, and the neutrons and protons into quarks, and so on and so on. And every single particle will be spread out, and it'll be so far from the next particle that it will never, ever come into contact with it. So effectively, all of time and space ends. There'll be nothing out there. It'll be stretched out so much. It's a bit like, if you can imagine, you took an orange juice that you made from squash. It's still orange juice. Now, can you imagine if you took that orange juice, I don't recommend you do this, but you took this orange juice down to the sea, to the Pacific Ocean, the biggest ocean in the earth, and poured the orange juice in. And the orange juice would spread out, and it would spread out and out and out and out, and all those little particles of orange juice would then be on their own. And the orange juice would cease to exist. All the particles would still be there, all the little tiny bits of orange juice that were, but they're spread out so much that it just doesn't exist anymore. And that's what would happen to all the atoms and the particles in the universe. All the energy will become heat energy. All matter will just become protons spread out across the vastness of space. That's the big rip. Now, if there's not enough energy to keep the expansion going, then the universe will stop expanding. It will grind to a halt, and gravity's still there, remember. It will start to collapse back in on itself. it would rush back in, and all of the planets and stars and everything would come back together again and collapse. And then who knows, maybe they might start expanding again. And then they would run out of energy and come back again, and it would collapse and expand and collapse and expand. And you get the idea. That's called the big crunch. It expands and it comes back together, and there's a big crunch. End of the universe. Okay. Wait for the next slide. For some reason, it's decided not to play. There he goes. So it's interesting. We don't know exactly how much dark. You can't see dark matter. It's not just dark because you can't see it. It's called dark matter because you can't detect it. It doesn't interfere with anything. It's there somewhere. The mathematics say they are. The universe is made up of about 4% normal matter and some energy, and about 95% of the universe is not there. We can't see it. It's hidden somewhere. It's called dark matter and dark energy. It must be there because the universe behaves like it is there. It's a bit like if somebody was invisible and moving a cup around. You know they were there because somebody was picking a cup up and moving it around. You couldn't see them, but you could see the cup move. So you know that there's somebody there moving it, but you can't see them. It's a bit like that with dark energy. It's there, but we can't detect it. We can't plug into it and use it to power our electric light bulbs, anything like that. It's called energy because it's making the universe do something. It's expanding it, but you can't use it like electrical energy. Dark matter and dark energy it's there in the universe, hidden somewhere. But scientists are actually looking for it. And when they do, it's going to give us the answer to how the universe is going to exist or cease existing. So scientists are currently looking at how to detect this matter and the energy, the dark matter, the dark energy. It's energy and matter you can't see, feel, smell, touch, hear, or otherwise find. It's a tricky one, isn't it? But once they found out how much dark energy there is, then we'll know which of those three endings is the one that's going to happen. Okay, right. Now the best bit about the universe is you live in it. And what's more, from where you are on Earth, you can see quite a bit of it too. So what's out there worth watching? So I thought the second bit of this lesson that we're going to do today is going to be about what you can do from where you are. When we return to Earth after our Across the Universe journey, you'll be able to look back and say, well, I've been out there, I know exactly what it's like. You may be able to tell someone, a friend, a family member, somebody, that something you can tell them about the universe. Okay, so we're going to look at stargazing or astronomy, maybe as a bit of a hobby. So if you like the universe and you enjoy living in it, why not go out there and look at it and enjoy it? Okay, so there's lots to see, and you can see most of it with the naked eye without anything. If you've got a good pair of binoculars, that's going to help you even more. And if you can't get one, a good reflector, if you can get one, a good reflector telescope, even more. So just pick a clear night with no moon, unless of course you want to look at the moon, and a place where there are no street lights, shops, offices, other buildings spilling their light into spoil the view, because you won't see so much. If you can think about it, if I'm trying to look at a very faint light in the distance and somebody holds a torch or a bulb in front of my eyes, I can't see it. So if you're trying to look at the stars, which are quite dim, and there's buildings with lights coming out the windows and people with bonfires in the gardens and a factory that's lit up 24/7 and street lights everywhere, you're going to block out so much you can see. It's going to spoil the view, definitely. So let's look at some of these, and we're going to start with the moon. The moon. I mean, you can see that without even a pair, but if you've got some binoculars, look at the moon or a telescope or something. It's amazing. Okay. Now, the face of the moon, that's the bit we always see, shows a completely battered surface. It's been colliding with asteroids and comets, and it's produced all those lumps and bumps, all the craters, and you can see them so easily. Just go out from your back garden on a clear night with a full moon or a half moon or whatever, and you can look up there and you can see those craters. Now, those craters are a testament to the bombardment that our own planet Earth has suffered. Now, the reason why the Earth and the moon have been bombarded is that they occupy the same part of the solar system. So the Earth was the target of the same swarm of debris, all the rocks and space stuff that's hit the moon. But on Earth, we have something called geological processes. We have volcanoes, we have the oceans, we have all sorts of things going on. And they constantly destroy the clues about the impact, because a crater, something will hit the Earth, a crater, and then the wind will come in, and the seas, it might rain, and eventually it smooths over. It's like repairing a cut or something. So on the moon, that doesn't happen. Like the Earth, for instance, where mountains rise up as tectonic plates move across, as continents crash into each other, the mountains rise up and they completely wipe out any evidence of craters or anything like that. We have erosion, volcanism, volcanoes, that sort of thing, other processes. So they cover up or consume those impact craters. So the record on Earth is limited to about 160 impact craters. That's the only surviving trace of millions of impact craters that have affected our planet. Now, there's one crater in particular. You can look at all of them on the moon, but one that you might want to go out and look at is called the Tycho crater. Why the Tycho crater? Well, it's easy to spot. It's got a very, very interesting pattern. You can see there's a blow up. It's down towards the middle, slightly to the left at the bottom on a bright spot. It's very easy to spot. And it's a favorite crater of moon watchers. Robotic spacecraft Survivor 7 landed just above it in 1968. It's one of the first places that we went to on the moon. So it's interesting. In addition to impact craters, you can also look at the moon and see it's composed, if you look on there, of light-coloured and dark-coloured material. So the light-coloured material is in the areas of the moon called the highlands, which represent the earliest crust on the moon. Impact cratering shattered this crust and often deformed it, pushing some of it into mountain high impact crater rims or rejecting it across the surface of the moon. Now, when the moon was relatively young, its interior was still molten. Consequently, magma, molten rock, sometimes rose and erupted onto the surface. And because of the bottoms of the impact basins were often the lowest place on the surface of the moon, the erupting lava would flow into them and begin to fill them. So the lava was similar to the rocks that you get from volcanoes on Earth. And like on Earth, they cooled to form a relatively dark-coloured rock. So for that reason, some of the largest impact crater basins are outlined by a ring of white mountains, the rim of the crater, and have floors of darker-coloured rock that's flooded the crater. And they're really good for looking at. Okay, so you've seen the moon. So you go out on 14 days later when the moon's gone, or another night when it's not in the sky, and you can look at some planets. So if you look up on a sky on a moonless night, hopefully, because the moon is very bright and it will block out a lot of other things you can see. Remember, a place with no or little light pollution. You can see billions of stars, all of which are in the Milky Way, all twinkling away like diamonds in the sky, as the song says. Now, you may notice that one or two of them are not really twinkling. Now, stars twinkle because the light from them has traveled vast distances and it comes through the atmosphere, so it's quite a weak light. Even though it's a star is a sun, it's like staring into a sun, but it's so far away, it's safe to look at the light from it. It won't harm you. So by the time it gets here, it's quite a weak light. And as it comes through the atmosphere, it gets moved around by all the different densities of the air, where you've got hot and cold air in there, and the light starts to twinkle a bit. But some of them don't twinkle, and that's because they're not quite so far away. They're very near. In fact, they're in our solar system, and they're the planets. And they move across the backdrop of the other stars. The whole stars tend to move together as one pattern, whereas the planets move around. That's why they're called planets. It's an old Greek word meaning wanderer, planet. And it means that they move around the stars. Okay. And they also have colors as well. Mars is red colored. And you can look at Mercury, Venus, Mars, Jupiter, Saturn, and Uranus, all visible to the naked eye, depending on the time of year and the time of day you're looking at them. And Neptune can be seen by those with very, very good eyesight, but it's just a tiny little dot. So on a clear night, when it's the right time of year, you can see the planets. Now, if you have a good telescope, you can also see the moons and the rings of the planets that have them. And if you research on the internet or get an app for your smartphone, you can easily locate them. Next clear, warm night, give it a try. See which planets you can see. Get out there, look in the right part of the sky. You'll actually find yourself away. If you get a nice star map and start to look for some of the constellations that I'll point out later to you, you can find things in the sky and you know where to look. If you've got one of those apps on your phone or your iPad or your whatever you've got, you can download it and you can literally hold it up to the sky and it will show you the stars, and they'll have all the names of them on there, all the constellations and the planets and satellites and everything you can look at. So you can look at stars as well. Now, the stars, all the stars you can see that are stars are in the Milky Way. Furthermore, they're all within a few light years of the Earth. You can actually see the Milky Way itself, of course. That band across the sky, that is the Milky Way. It's where the plane of our galaxy is. So if you can imagine our galaxy was like a big dish of swirling stars, that's the main plane of our galaxy. All the other stars are just those around our little bit here. And they peter out as they get away from that main bit. That's why you can see that really strong bit in the middle. Okay, so let's have a look at what we're doing. So you can go out there and try and identify some of the individual stars, again using an app. You can try and find the pole star or the North Star. You can find your way around the heavens by looking at patterns of stars as they appear in the sky. Now these patterns are called constellations. Now they were named by our ancestors, and they're supposed to look like animals and objects in the sky and people. Now, a word of warning about constellations. They don't actually exist in reality. They're just patterns that appear as they do from the Earth. In reality, the stars in a constellation are all over the place. They're three-dimensional, but from where we are, it's just a coincidence that they look like they do, and only here. So I've come up with 3 constellations you could look out for. Okay, there are many, many more. If you get a good star map, or you go on the internet, do some research, you'll find even more to look at. But these are the ones that are a good start. If you can find these, you're doing pretty well. So there are all of the constellations. As you can see, they've got funny names: Draco, Camelopardalis, Cassiopeia, Perseus, Sagittarius, all those things, Cygnus, the swan. They're supposed to represent things, people. Okay, so let's have a look at one you can spot, and you will probably know this one. You've got Ursa Major, Cassiopeia, and Orion. So we're going to look at one or two. So what have we got here? We've got that is Ursa Major. Now, the easiest bit to spot is that little square that I put on the slide there to the bottom left. That's the bit to look for. The whole constellation is the main picture. But if you can find that thing that looks a bit like a saucepan, sometimes called the plough, then that is the Great Bear. Now, if you look at the way that the patterns are drawn on there, ancient man thought that that resembled a bear. I can't see it myself. I suppose the back legs are on the left, one leg on the right, tail at the back, and that pointy thing that looks a bit like a space rocket shape is the body of the bear, I guess. But those stars only look like that from the Earth. If you were to travel a few light years to one side, that shape wouldn't exist. It would look like something completely different. And those stars are vast distances away from each other in 3 dimensions. They just literally look like that because they're particularly bright, and people have drawn a pattern on there. Another one you can look at is, let's have a look, is Cassiopeia. That's like an upside down W. That's always a good one to look at. That's fairly clear to see on most nights. And these 3 constellations I'm showing you are actually quite easy to see on a night that's not quite so clear, and maybe there's a bit of light pollution as well. So I've picked them because they are easy to spot. And then we have Orion. Now with Orion, see the 3 stars in the middle, that's the belt of Orion. You can see it's supposed to be someone with a bow, just about to draw back and fight. So Orion the hunter. But again, that's sort of 3 stars along the middle, the belt of Orion. And the 2 at the top and the 2 at the bottom, that sort of trapezium shape. That's the bit to spot for. You can see that quite easily. The star in the belt across the middle, the 3 stars are going sort of from 8 o'clock to 2 o'clock. The left one there is a star called Betelgeuse. That's the star that's very, very soon, astronomically speaking, very soon, but anything between now, tonight, and the next few million years, that looks like it's about to go supernova. Now, bearing in mind how far away it is, it probably already has, but the light's still reaching us. So if you look at these stars, you can also find out how far away they are in light years. So you can look at a star and say, that's amazing, that's 500 light years away. When that star, the photons, the light I'm looking at that star from now left the star, Henry VIII was king, or the Battle of Hastings was being fought, or it was before the birth of Jesus, or it was the dinosaurs are walking the earth, that sort of thing. You can really think then, and it's quite incredible when you look and see how far back in time you go. Okay, so galaxies. You can see some galaxies as well. You can see one or two. You can see some with or without a telescope. Using a telescope is best. Our nearest neighbours, as we already mentioned last week, were the Large and Small Magellanic Clouds. They're easy to see from the southern hemisphere, so if you're on holiday now and south. But one of the most beautiful galaxies we can see with the naked eye is visible in the night sky, usually not until later in the year. It's called Andromeda. The naked eye on dark moonless nights, and the Andromeda galaxy is the only other, besides the Milky Way that we're in, it's the only other spiral galaxy we can see with the naked eye. Now, a little word of warning, you might want to get prepared for this, but Andromeda is heading towards us at 110 kilometers per second, 68 miles per second, and we're going to collide with it in about 4 billion years. So if we are still around then, or our descendants are, we're either going to have a spectacular view of one of the most amazing sights in the universe, two galaxies colliding. Of course, by then the sun's probably going to go to red giant, so the Earth may not even exist then, but you know, who knows. That's not the end of it. There are lots more other things to see. See satellites orbiting. You can look at the International Space Station. If you've got an app, a good app, a stargazing app, then it will tell you when it's coming over, and you can look up and you can see a bright light going across the site, and that's the ISS. You can look at other satellites. There's loads and loads of satellites up there, and with a good telescope or good pair of binoculars, amazing. You can also look at the supernovae remnants, the nebulae. You might be able to see a comet if one comes around. Meteors, particularly if the right time of year in the right part of the sky, you can see lots of meteors, and you can see all sorts of stuff out there. So just get out there, grab a good astronomy book, a star map, and or an app, get stargazing. Okay, so now we've seen the universe from Earth, all the way out from Earth to the universe. There's a question that really needs asking, and that is, are we alone? So, next time we're going to look at the possibility of there being life, whether we'll ever meet it, and what if we did, what would it look like or seem like? Now, without giving too much away from next week, if you think about the different variations of life on Earth, and that's just on one planet, that's an amazing array of people, you know, of animals. You think we've got humans, we've got snakes, lizards, we've got insects, we've got all sorts of things. So alien life out in the universe, what's it going to be like? Well, we're going to look at that. We're going to look at what the chances are. We're going to find out what something called an exoplanet is. What something strange called the Goldilocks zone is. Think about that. And exactly how many planets there may be out there. Okay, but until then, I want you to have a good stargaze. It's a bit cloudy today where I am, but there's some blue sky, so you may be in luck tonight. You never know. Enjoy the universe as we travel through it. And you're traveling, in actual fact, you don't need to leave the Earth to travel through the universe. We'll find that out as well. You are already sitting on an amazing space-time machine. It's called the Earth. And it's what you're traveling on. You were born onto. It's traveling at incredible speeds across the universe. It's got a massive open window called the sky that you can look out and see all of the universe. And even though you may or may not ever get into space yourself, or even get particularly far away from Earth, if you do, there's still so much to look out there. So next week, we are going to, as I say, we're going to be looking at life in the universe. We're going to look at how life started on Earth, and then we're going to see if the chances of that happening. What do we need for life to take place? What chemicals do we need in place? What processes? Where does the energy come from life? Why did life come about in the first place? Who knows? We don't know. Why is it not really what we're here for? But we look about how life started. We'll have to go to the bottom of the deepest oceans, to volcanic vents, and see how ordinary molecules started reproducing themselves and came together to form complex life molecules that turned into single cells, that's multiple cells, and gradually turned into all of the different types of animals there are that live under the sea, in ice, up in the upper atmosphere, on the land, in deserts, in Antarctica, all the life forms that have adapted. And then we're going to look and see how would that pan out if we were to look at the rest of the universe. Amazing and incredible thing. Okay, until then, have a stargaze, enjoy the universe, and come back next week. We've got time now for some questions and answers and that sort of thing. But I hope you've enjoyed thinking about the universe. If only you take one thing away, how big. Remember, space is big. The universe is massive. Millions and billions of light years across. Light from parts of the universe will never, ever get to where we are. There's a visible end to the universe, but there might be even more beyond that, and we will never, ever be able to get there. It's physically impossible. Okay, right, let's see if I can unmute you. Where's the participants? And see if anybody's got any questions or anything, because that's what it's all about. Eden.
No questions.
No, I hope you enjoyed it. It's an amazing place, the universe.
Yeah, I guess.
Yeah. What did we do last week? We were going to do models of the galaxies, weren't we? Did anyone build a galaxy model?
Sadly, no. Only built a rocket on the lessons. So.
Well, who's going to go stargazing the next time they can?
I guess I'll do it. I'll try.
Yeah. If you go to just Google or one of the search engines and do star map, you can order books online, that sort of thing. But you can get an idea of them if you can. There's some fantastic apps that you just literally take your phone out or your smartphone or your tablet, and you can hold it up to the sky, and it knows exactly which direction you're looking at, and it shows you all the stars you're looking at with all their names on, and you can really see them. It's amazing. And if you've got some binoculars, you know, you can see even more. But yeah, it's well worth it. There's loads to see. It's amazing. Okay, right. So I hope you've enjoyed this one. We've got another 2 to go. So next week it's going to be alien life, and then the week after we're going to be learning about time and some of the things that we can do. Maybe a little bit more about black holes, a little bit more about what time is, how we measure it, all sorts of things. Possibly some nice time travel-y bits as well. Oh, who was that? Somebody said something? Oh, no. Okay, if there are no questions or anything, I would like, when I come back next week, to hear some amazing tales of what you've seen in the sky. I'd love to find out some of you been stargazing and see if you saw anything. Even if you just saw the crater, Tycho crater on the moon, and maybe Venus, a nice bright star in the evening sky. Have a look at something. Come back and tell me what you've seen next week. And I'll see you in a week's time. So take care, stay healthy, and bye for now. Cheers. Bye.